Welcome to Solving Radical Equations. Before we dive into solving radical equations, let's do a quick review of rational exponents. So not too long ago we saw that radicals can be written as a base with a power that's written as a fraction. So a square root is the same as saying 2 to the 1/2. Cube root of x to the 1 is x to the 1/3. When these radicals are written as rational powers, we can apply power rules. So here are a few examples of a base with a power to a power. We would be multiplying the powers. We would get 3 to the 1/2 times 2 over 1 would equal 3 to the 2 over 2, which equals 3 to the 1, or just 3. Similarly here, 2 to the 1/3 times 3 over 1 would equal 2 to the 3 over 3, which equals 2 to the 1. And then here we can venture that we're going to get x to the 4 over 4, which will equal x to the 1. Keeping this in mind, when we look at this now here in radical form, we know that this can be written as 3 to the 1/2. So 3 to the 1/2, all to the power of 2, we know is going to get us 3 to the 1. So that is why here, that's exactly what's going to happen is when you take the square root and you raise it to the power of 2, really this is what's happening here. You don't have to write it in this form. I'm not going to necessarily make you write it in the rational exponent form, but this explains here why you're going to get 3 to the 1 when you do the power of 2 with the square root. And keep in mind that the power and the certain roots are opposite of each other. So because this here has the index of 2, the square root and the power of 2 cancel each other out. Okay, and it all comes down to because of this reason right here. So we're going to use that idea today as we're solving for a variable that's under the radical. So very, very basic example here. I'm solving for x. It's under a radical. I want to get rid of the radical so that I can get x out from under the radical in order to solve for it. So I'm going to use that trick where I'm going to square the square root. And that will cancel the root, and that will give me x outside of the root. But of course, in an equation, we're going to want to make sure we do the same thing to the other side. If I'm going to square the square root, I need to square the other side of the equation here. And that's how I'm going to get an answer of 9 for x. Okay, please take a second, pause the video so you can record the overall process. You have to remember we're working with equations. So what you do to one side of the equation, you always have to do to the other. So adding to one side, add to the other. If you're squaring one side, you got to square the other, etc. So step number 1, you want to make sure that all outside values of the radical are on the other side of the equation. You want to isolate the root, and everything under it stays under the root. But anything outside, add the opposite to the other side or divide to the other side to just get the root by itself. Step 2 is you're going to undo the root by raising it to the power that's the same matching power to the root. Okay, the same index value, so the power. Square will undo the square root, cube will undo the cube root, etc. Once the root is gone, you can do step 3, which is solve for the variable. And then you should check your answer because not all solutions will work. And a little rule here that I have in red, very important, is keep in mind that if you're working with the square root, you can't have the square root equal a negative value. Otherwise, there's no solution. We saw that before. if you have the square root of x equals a -2, you know that that's not possible. There's no possible value for x that you square root and get a negative answer. So that would be no solution. And you could technically stop right there and stop solving. Here's our first example. Square root of y minus 2 minus 1 equals 5. What you need to notice is that there's a bunch of stuff under the radical that stays together. So outside values here is the -1, the -1. And that's what we need to do in the first step, is we're going to have to add that value to both sides of the equation so that we get just the root alone. And this will be 6. In the second step, we're going to undo the root. We want to get rid of that radical. And so we notice this is a square root. So what we're going to do is we're going to square it so that it cancels the root. Everything underneath stays the same. You're not squaring what's under it. You're squaring the symbol itself to cancel it out. But what you do to one side, you have to do the other. So I have to square the 6, and that becomes 36. And then step 3 is solve for the variable, in this case y. So I'm going to add 2 to both sides. And I'm going to get y equals 38. And then in the last step, I'm going to want to check to see if 38 really works. And when you check it, please put it back, way back at the beginning here. So I have the square root of 38 minus 2 minus 1. And I'm checking to see if that all comes out to 5. So 38 minus 2 is going to give me 36. And then when I square root 36, I'm going to get 6. When I minus 1, I get 5. And that checks out to the answer that was posted at the beginning of the problem, right here. A new example. Cube root of d plus 2 equals 7. Isolate the root. So anything outside of the root on the left-hand side here of the equation needs to move to the other side. In this case, there is nothing to move. It's already isolated. So now what we're going to need to do is get rid of the radical, which in this case is a cube root, which means we're going to need the power of 3 to undo this kind of root. What you do to one side, you got to do to the other. So you got to remember that d plus 2 does not get cubed. It's going to come down and just be outside of the box. 7 to the power of 3 you could look up on your power table if you have one, or just take the calculator. It's 343. Now we're at the third step, which is solve for the variable. So d here is going to equal 341. And then please take a second to check it. I'm going to put it back at the beginning of the problem, which is the cube root of d plus 2, so 341 plus 2, which will give us cube root of 343. And then if you take your power table or a calculator and cube root this, you're going to get 7, which checks out to the answer we're supposed to get. Here's a second kind of problem we're going to encounter. A square root equals a square root. So in these cases, I'm not going to give you problems where you're going to have stuff on the outside to isolate or move to the other side. There technically exists such a problem, but it's kind of a much more challenging problem. So in this case, we're jumping right into step 2, which is get rid of the root. This is a square root, so you're going to undo this square root with a square and the same power on the other side. And that will be the case. I'll always give you the same kind of radical on both sides. So your radicals will cancel out, or your square roots will cancel out. You'll have your radicands, which are these expressions on each side, left over. Okay, so now we're just back to a regular algebra equation. Get the x's on one side. So I'll bring the smaller x over here. That'll give me a 4x. That means I'm bringing this 4 to the other side. Divide by 4. 14 over 4 is reduced to 7/2. You can get a decimal if you'd like. And then I need to check to see if the 7/2 actually works. I'm going to put that back at the beginning of the problem. This one doesn't look too pretty here, but it is what it is. So does that amount equal that amount? Notice here I have to substitute it in both sides of the equation. So when you multiply here, you're going to get 2 goes into 6 3 times, 21 minus 4. And then here you're going to get 7 plus 10. And you just continue simplifying. You're checking to see if the left side equals the right side. 21 minus 4 is 17. And 7 plus 10 is 17. And you get the square root of 17 equals the square root of 17, which tells you your 7/2 is a correct answer. Another example that's a little bit different, and that's why I continue giving more examples here, because I want to make sure you get a taste of a little bit of everything you might encounter. V to the 1/2 plus 1 equals 0. So sneaky here is the radical hidden as the rational exponent. We know now that this is the same as saying square root of V plus 1 equals 0. So it's up to you if you want to work in the exponent form or the radical form. But we need to isolate the radical, so we're going to have to subtract 1 to the other side. And so we have the square root of V equals -1. And this is where you're supposed to notice, uh-oh, the square root equals a negative number. No solution. Okay? And you're technically supposed to stop. But let's say you don't recognize that. You're going to proceed on with the process. So I'm going to put a little mark here. Technically, if you're bright enough to note that, you can stop there and you're done. You just got to make sure you tell me on paper, no solution. But if you don't catch it now, hopefully you'll catch it in the check, because you're going to continue on. You're going to say, all right, I'm going to square that. And if you do everything correct, you're going to get V equals +1. And you're already going to be solved. You're going to go and put it in your check. And so you're going to put it back and say square root of 1 plus 1 equals 0. This is, I guess I'm using this step right here, which is okay. You could use either the beginning or the radical version. The square root of 1 is 1 plus 1. And you'll have 2 equals 0, which is a false statement because 2 does not equal 0. And at this point, you could recognize, ooh, I don't have a solution here. Okay, so at either point, you should be able to recognize that there's no solution to this problem. It'd be great if you would recognize it here. If not, you should recognize it in your step, and that is why I make you check it at the end of the problem. A solution that does not work is called an extraneous solution. It's just a fancy word for a special value that does not satisfy the original equation. And that is all that I have for examples at the moment. We'll do a few more examples in class.